All right, so this lecture is a review of everything we have learned in this class, actually a subset of what we learned in this class that I particularly listed here to be the content that may goes into the final exam. All right, and so the format of this class is the following. I'm going to go through all the topics and very quickly, so if you have any questions or clarifications you want me to go through in more detail, please interrupt me. Otherwise, I'll go through all these topics, and at 3:30, our project TA, Phil Kaplan, is going to come here and answer any remaining questions about the projects. All right. So the first thing we did in this class is ordinary differential equations. So numerical methods for solving them. And in the beginning, we have outlined for any numerical methods, what do we really want to understand about it? So the first thing is accuracy. The accuracy aspects is going to actually permeates throughout the entire lecture, starting from ODE, PDEs, and terminates at Monte Carlo methods and statistical learning. So everything we do, we are concerned about accuracy, because as soon as we start using numerical methods, we are no longer computing things exactly. And the amount of error we're making is a crucial aspect of the field called the numerical analysis. That is basically performing analysis to figure out how accurate the approximations are. So in ordinary differential equations, we figured out accuracy of our approximation to time derivatives through Taylor series analysis. So the Taylor series analysis is also a primary tool for us to analyze accuracy of finite difference, ODEs, and also, although we haven't talked about it, Taylor series can also be used to analyze the accuracy of finite volume and finite element methods. So this is one of the tools you should be able to use fluently after taking this class. So that's for accuracy. Another aspect of accuracy is the link between accuracy in approximating the derivative, okay, and the accuracy in obtaining the final solution of the ordinary differential equation. So what's the relation between these two accuracies? Yeah.
If the scheme is stable, will be the same one?
Yes, it's stability. So that's the next topic, zero stability. Actually, the order of accuracy can be shown to be the same if you have zero stability. Although it's by itself, it's often not sufficient. So what does zero stability mean? That's something you should also understand, right? It means the scheme is stable when solving du dt equal to 0, right? So that's a very elementary requirement on the scheme. If the scheme is not zero stable, it's not good for anything, period. So that's basically knowing what it is and being able to analyze zero stability. Eigenvalue stability is a more complex concept. So eigenvalue stability is the critical thing to understand about eigenvalue stability is the concept of a stability region. So the stability region is usually in the space of real of lambda delta t and imaginary of lambda delta t for solving the differential equation du dt equal to lambda u. And the different schemes have different stability regions. For example, forward Euler has this, right? And having a different scheme, for example, some kind of a Runge-Kutta scheme has this type of stability regions over here. And implicit schemes usually have much larger stability regions, right? Yes?
I remember once in class you made a comment about like if the scheme is higher order, it has a certain behavior at the
origin
axis.
Yes. Yes.
What is that behavior?
Okay. So you can see how so first of all the stability region can be applied to a scheme for solving differential equations. It can also be applied to the imaginary scheme of an exact solver. So imagine you can solve a differential equation exactly. What is the stability region? Yeah, that's the entire left plane, right? So if you have exact solution of du dt equal to lambda u, then the solution would decay to 0 if and only if my lambda has a negative real component. So a higher order scheme has a better approximation to that behavior around the origin. So if you zoom into the origin, okay, a first order scheme would have a stability region that is tangent. But the second order derivative may not be 0. I mean, if you look at that, the boundary of the exact scheme, the boundary has a 0 first order. I mean, it's the first, the tangent is straight. It has no curvature, right? It has no bend. I mean, if you take a third order, fourth order derivative, it is always going to be 0. It's a straight line. And a higher order scheme has a better approximation to this behavior in the origin. Okay, so that's basically it. Yeah.
So how do you explain like the part of the, like for example, the wrong method, there's some stability in the right half plane, even though the exact solver it only has stability in the left half plane?
Yeah, so the Runge-Kutta scheme is not an exact solver, right? So if you zoom into this region, the Runge-Kutta scheme is actually going to have a 0 curvature, unlike this the forward order, which has finite curvature. But away from here, when your delta t is so large that the accuracy of the scheme actually only concerns the behavior of the scheme when delta t goes to 0, right? So when you're in this region, delta t is so large compared to lambda that the order of the scheme doesn't really matter anymore. So you can construct you can actually construct Runge-Kutta schemes that are horrible in this region. I mean, you can have stability regions that are a lot smaller than this. But this type of Runge-Kutta scheme, the reason it is popular is because it includes a significant portion of the imaginary axis in its stability region.
So like the stability in the right half plane is unphysical.
Yeah, it's unphysical in some sense. Yeah, right. It's not saying it's undesirable. In many cases, it's actually desirable, right? But you're going to get a wrong solution. The real solution over here is actually going to be divergent, but you're going to actually get a convergent solution. So that actually manifests itself in many CFD flow solutions. So you can solve for flow, and the flow would actually physically may be unstable. It can produce this vortex shedding, and I mean, if you look at the real flow, it may be unsteady. But you can use a CFD solver that you actually get a steady state flow, right? So these are one of the reasons you would get a steady state flow out of a real flow that may actually be unsteady. All right. Any other questions?